In this video, we will learn how to compute the distance using lines and planes. A few ideas that we've covered so far are going to come together in these problems, and that's the idea of distance, as well as points, lines, and planes. Each problem will present us with different information, and we have to figure out how to take that information, put it together to find the distance they are asking for. In our first example, they ask us to find the distance from the point 1, negative 1, 3 to the plane 4x plus y minus 2z equals 1. Before we jump in and do any math, let's draw a picture out so we can visualize what exactly we are looking for. So we have a plane here, and we have a point in space that's not on the plane. We can confirm the point is not on the plane by plugging the point into the equation of the plane. So here we would have 4, minus 1 is 3, minus 6 would be negative 3, which is not equal to 1. Always helpful to check for that, since if the point was on the plane, the distance would be 0, and that would be it. So we are looking, if we drop a perpendicular down, that would be the shortest distance from the point to the plane. Right, so this here is our distance. So how are we going to go about finding that distance? What do we know? What are we missing? What can we find? So we have a plane, so we know that there's a normal vector, and I can draw that normal vector anywhere on the plane, so I'm going to draw it perfectly over that distance. Now I'm not sure, the normal vector might be longer than the distance we're looking for, it might be shorter. In the diagram I drew it shorter, but the normal vector would be right on top of that distance, which is extremely helpful for us. And remember, vectors aren't fixed in space. So the first way we could approach this problem would be to write an equation of a line that is perpendicular to the plane that goes through that point. Right? So our first thing would be equation of the line perpendicular to the plane. Okay, so all that means, just to really clarify, that would mean our direction vector for the line would be equal to the normal vector of the plane. Once we have that equation, whether we write that as a vector equation or parametric equations, then we would look for the point of intersection. Point of intersection between the line and the plane. And then once we have the point in space and the point right below it, by the point of intersection, we would use our distance formula. So that is a completely valid method. It uses tools that we have and we have used previously, but it is not the way that I'm going to solve this particular problem. I'm instead going to opt for a second approach, and the second approach is using a scalar projection. I personally think it's a little bit more efficient of a method, and it works quite nicely once you get all the pieces together. But what we wrote in blue as the first method would work perfectly every time. Okay, so as far as a scalar projection, we need two vectors where one is being projected onto the other. Well, we already have one vector in our diagram, which is a normal vector, which happens to be right over that distance that we're looking for. So that's really helpful because the normal vector can then serve as the vector we're projecting onto, right? So we're going onto the normal vector. Now the question is, what vector are we projecting onto that normal vector? So a plane is really just a collection of points. So if we can find one point on the plane and then draw a vector or create a vector from the point on the plane to the point in space, I'll really make that a little bit larger, the point, we'll call that vector v, and we can project vector v onto the normal vector. And the nice part here is there are an infinite number of points that we can figure out. We just need one of those points. Point on the plane, point in space, create a vector, compute the scalar projection of v onto n. One slight adjustment we have to make is we do have to take the absolute value, since a scalar projection could be negative. Okay, so that means the distance is the absolute value of the scalar projection of v onto n. Okay, so we have a plan. Now let's actually find all of the pieces. So the normal vector here, coefficients of the plane, so 4, 1, negative 2. We need that vector v. Okay, so the point on the plane, this is just a matter of trial and error. So looking at the values of x, y, z and their coefficients, 0, 1, 0 to me stands out as a point on the plane. You might have thought of a different point. As long as it works in the equation of the plane, it would work in this computation. So now we need to create vector v. So vector v is going to go, we'll use the point 1, negative 1, 3 as the terminal point, and 0, 1, 0 as the initial point. So 1 minus 0, negative 1 minus 1, and 3 minus 0. So vector v is 1, negative 2, 3. And now we're going to find the distance, which is the absolute value of the component, or the scalar projection of v onto n. So that is v dotted with n over the magnitude of n, since that's the vector we're projecting onto. That's the vector we want to be a unit vector. So it does look like we need one more piece of information, which is the magnitude of the normal vector. I'll use the space here. So that's going to be the square root of 4 squared, so 16. 1 squared is 1. Negative 2 squared would be 4. So the magnitude of the normal vector is the square root of 21. Okay, and again, it's the absolute value of that dot product. So we have the absolute value of 4 minus 2 minus 6 over the square root of 21. So that's going to be negative 4. Absolute value would be positive 4 over the square root of 21. So there's the distance from the point, in this case 1, negative 1, 3, to the plane 4x plus y minus 2z equals 1. Okay. Now our second example, find the distance between the planes 2x minus 3y minus z equals 5 and 2x minus 3 minus z equals negative 8. So the first thing to notice is we have parallel planes. Important to notice, because how we notice that is their coefficients are the same in this case, or they could be scalar multiples of one another. And reason that's important is if the planes were not parallel, then that means they're intersecting, which means the minimum distance between the planes would be 0. We'd have way less work to do. But in this case, we do have two parallel planes. We can draw them out so we can get an idea here. Okay, so we have two planes. Let's say from this point to this point, if we drop perpendicular, that's the distance we're looking for, right? That would be perpendicular. We still have that normal vector. In this case, we have two normal vectors, one off of each plane, and we want to find that distance. So essentially, we can make this problem easier and relate it to the problem that we just completed. If we find a single point on the first plane, then all we have to do is find the distance from that point to the other plane, which is exactly like what we did in the first example, right? So the plane I underlined in red, point on that plane would be, I'm seeing 1, negative 1, 0 as a point. There are many others, but that's what I see. 2 plus 3 minus 0 would be 5. And then we're going to need a point on the other plane anyway. So point on that plane would be, I see negative 4, 0, 0. I guess 0, 0, 8 would also work. That would be an easy one, and I'm sure there are plenty of others. Okay, so parallel planes, we want to reduce 2 point and a plane. And the way we do that, find a point on one of the planes, and there we go. We have a point, we have the other plane. So now would be a good opportunity to pause the video. From this point, see if you can pick it up, find the distance, and then play the video to see how you did. Okay, so hopefully you try this on your own. So distance, not a vector, distance is a scalar. Distance is going to be the absolute value of that scalar projection of v onto n. We do need to figure out what v is, right? So let's say that's the point. There's the point on the other plane. There's vector v. So vector v will go red to green. So that's 1 minus -4, -1 minus 0, not comma 0. -1 minus 0, and 0 minus 0. So vector v is 5, -1, 0. And the normal vector is 2, -3, -1. We are going to need the magnitude of that normal vector. So we'll compute that right now. So 2 squared is 4, -3 squared is 9, -1 squared is 1. So magnitude of that normal vector, square root of 14. So the distance, I'll go back to green now, distance is absolute value of 10 plus 3 plus 0 over the square root of 14, which is 13 over the square root of 14. Okay, so we just completed 2 different examples with 2 different given information sets, and we wound up computing them the same way, right? A point to a plane or a plane to a plane, we follow the same steps. Now, what if they ask us to find the distance from the point, -2, 1, 2, to the line, x equals 3t, y equals 1 minus t, and z equals t plus 1? So we don't have a normal vector, so we're going to have to make an adjustment to our approach here. Again, let's start with a picture to get a sense of what we're looking at. So we have our line, label that L, and we have our point in space. Okay. On the line, we can find a point, and we can also find a direction vector, just to include some of the information that we would be able to pull out rather easily. Now, unfortunately, looking at all of this combined together, I don't see a particularly easy way to go and find the distance, which in this case, if we drop a perpendicular down, right, this is the distance. Now, please let's not confuse ourselves between the distance and the direction vector d. Important that our notation has the vector hat there so that we know that those are separate values. Okay, also direction vector doesn't have to be perfectly the length here. It could be longer, it could be shorter, the same way with the normal vector. Okay, so again, we have a few options. So one thing we can do is create a vector from the point on the line, or a point on the line, to the point in space. Call that vector v. So our first method, we can use the Pythagorean theorem. So we can find the magnitude of vector v. We can find the magnitude of the scalar projection. I know in this case in the diagram, I did draw the direction vector to perfectly be that length, but it does not have to be. Okay, it could very much be the case that the direction vector is, let's say, there, and then our line extends out, right? And we would have to do the scalar projection. So we'd have length of the hypotenuse, we'd have the length of one leg, and then the Pythagorean theorem would allow us to solve for the other leg, which in this case is the distance. So that is our first option. It works perfectly well. I think there's a lot of work that goes into that computation, but it would get the correct answer. Now, the second approach here is with area of a parallelogram. Okay, so if we took vector v, and I'm going to go from the end of the direction vector. All right, so there's vector v. I can slide that over, and I can put the direction vector there. Vectors are not fixed in space, so we're able to do that. So now we have this parallelogram. We know how to find the area of it using vectors. It is the magnitude of the cross product of the two vectors. Now, how does this help us find the distance? Well, the other way we know to find the area of a parallelogram in a simpler geometric sense is area of the base times the height, which in this case, the area of the base is the direction vector, and the height is the distance that we're looking for. So we want to find the area of the parallelogram and then solve for the height, right? So this distance would be the height of the parallelogram. So first thing we need to do is find the area of the parallelogram. So if we remember, the area of the parallelogram is going to be the magnitude of v crossed with d. So that means we need to find vector v and vector d. So vector v, so a point on the line here, so a point on the line would be 0, 1, 1 if t equals 0. Then we have our other point, negative 2, 1, 2. So we'll go point to the point on the line, so negative 2 minus 0. So this point is the terminal point. I should be more specific there. 1 minus 1 and 2 minus 1. So vector v is negative 2, 0, 1. The direction vector is the coefficients of t in the equation of the line. So 3, negative 1, 1. 3, negative 1, 1. So now we have a cross product to complete. So v crossed with d, I, j, k, negative 2, 0, 1, 3, negative 1, 1. Another good opportunity to pause the video and practice computing a cross product, and then play the video when you're done. Okay, so you should have found 1, 5, 2 to be your cross product vector. So the magnitude of that cross product vector is the square root of 1 plus 25 plus 4. So the square root of 30. So up here, square root of 30. And then as we said, the other way to find area of a parallelogram is base times height. So we know the area is square root of 30. The base, in this case, is the direction vector. So the magnitude of the direction vector is 9 plus 1 plus 1. So the magnitude of the direction vector is the square root of 11. So square root of 11 times the height. So height equals square root of 30 over the square root of 11. And that's our distance. Okay, so the distance from the point to the given line is the square root of 30 over square root of 11. So in this example, we took a different approach. We had to use the area of the parallelogram, which brought in cross products and the magnitude of the cross product representing the area of that parallelogram, and a little bit of old geometry, right? The area of a parallelogram being the base times the height, figuring out what vectors stood in place of base and height, and using that to find our distance. The last example is finding the distance between skew lines. It is the most challenging example because there is the most work to do, not because it's difficult to understand conceptually. So if we remember, skew lines are lines that are not parallel and also don't intersect. They exist in parallel planes. So if we draw this out, we have two parallel planes. We have already found the distance between parallel planes. So at a certain point, we're going to reflect back to that second example that we did. We just have to get to that point. Right, so skew lines means, let's say we have this diagonal here and that diagonal here. They're not parallel, they don't intersect, therefore they are skew. And we can check that algebraically. We learned how to do that. Now we want to find the distance, basically, between the two parallel planes. So let's suppose, just for visual sake, if these 2 points are right on top of each other, right, that's perpendicular to both pieces, this is the distance we're looking for. Okay, since skew lines exist in parallel planes, we need all the information we had in that example where we looked at a point to a plane and then take that to actually find our distance. But now the question is, how do we get that information? In order to do that, we did a scalar projection. We projected onto a normal vector. So let's just stop there. We don't have a normal vector, so we need to figure out how to create one. Right? So how do we create a normal vector? Okay, so let's just write out what we talked about for our notes. So we want to reduce this, reduce to distance between parallel planes, okay, which means we need a normal vector. Okay, so what information do we know? Off the lines, we know that there's a point on this line, and we know there's a point on this line, right? They don't necessarily have to be the closest points. We just know 2 points, a red point on the first line, a purple point on the second. We also know that there's a direction vector. We'll call this direction vector 1. And then there's a direction vector here. We'll call that direction vector 2. Let's see if I can clean that notation up. Direction vector 2. Okay. It would be really helpful if those two vectors were in the same plane, because when vectors are in the same plane, we can take their cross product. But that's easy enough to solve because vectors aren't fixed in space. So we can take that first direction vector and just drop it onto the second plane. So we can say, okay, there's the second direction vector, and I should probably not go off the plane. Let's keep it on the plane there. We can cross those two direction vectors, and that would give us a normal vector, which we then can move so that it lines up on that distance that we're looking for. And then we can connect. Let's do that. Let's not get too far ahead of ourselves. So we're going to need a normal vector. So cross the two direction vectors. Okay, so our normal vector is the cross product of the two direction vectors. So I, j, k. So the first direction vector, coefficients of t, 1, negative 2, 1. Second direction vector is coefficient of s's, 2, 1, negative 3. Now in a problem, they may use the same parameter t for both lines. Understand that they are separate parameters for each line. In this case, they do separate and make distinct parameters for each line. So we have 1, negative 2, 1, 2, 1, negative 3. Okay, so cross product here is going to be 5, 5, 5. Right? 6 minus 1 would be 5. Negative 3 minus 2 is negative 5, but the j component's negative. And then 1 minus negative 4 would be 5. Whether you use cofactor expansion or the diagonal method, make sure we feel proficient at finding the cross product of two vectors. Okay, so we have our normal vector. Now, we can connect the 2 points we know. So that red and that purple point, we can connect those vectors. We'll call that vector v. Our diagram's getting pretty busy now because all the work we had to put in to find all the information, right? We started with direction vectors and points on lines. We combined them to get a normal vector, right? So that took a bit of work. Now we're connecting 2 points, one on each line, which is essentially one on each plane, to create a vector v. So the point on the first line, if t is 0, that makes it 4, -8, 0. And then a point on the second line, if s is 0, that's 3, -1, -3. Right, so this was t equals 0, and this was s equals 0. So our vector v then is 4 minus 3, -8 plus 1, and then 0 minus -3, so 0 plus 3. So we have 1, -7, 3. Now we have all the information we need if we think back to that second problem that we completed. So the distance we're looking for is the absolute value of the scalar projection of v onto the normal vector n. So that's the absolute value of the dot product of these two vectors. So 5 minus 35 plus 15 over the magnitude of the normal vector. So let's find that. So that's the square root of 25 plus 25 plus 25. Magnitude of normal vector, square root of 75, which we can reduce. So that's 5 square root of 3, right? Square root of 25 times the square root of 3. Reason for reducing that is we might be able to simplify the distance value. So we get negative 15. Absolute value is positive 15 over 5 square root of 3. So reducing that, 5 over the square root of 3 would be our distance. So that is how we compute the distance using points, lines, and planes. I would encourage you to go back to those first examples where we wrote out a few different methods and try the other method. See if you get the same answer, and maybe that approach makes more sense to you. But practice. Do more of these problems to get comfortable with finding these distances and using the different tools that we covered in the video.